Dr. Tripathy, he's also from NCPR. He'll be talking about summer variability in bio-optical properties.
Thank you, Chairs. Good afternoon to all. At the outset, I would like to thank SaGAA for giving me this opportunity to share this dais. So I'll be talking about the bio-optical properties and phytoplankton pigment signature. So bio-optical properties are nothing but the constituents which are present in water, and that modulates the underwater light field, because we know light is one of the essential factor for carbon fixation in the ocean. And I'll be talking about how the phytoplankton pigments vary in the Arctic fjords. As we know that Arctic is amplification is happening, means Arctic is warming much faster than the rest of the globe, and as said by previous speakers in the morning, that it is maybe sometimes 2 to 3 times or maybe sometimes 4 times, and it is expected that by 2050 there will be no ice in Arctic in summer. So what happens? I'm not going to talk about the Arctic ice decline or about that. What is the impact of ice declining on the fjords? I'll be talking about that. So in summer, the impact of temperature rising is much more than the other seasons. So what we are going to explain here is how the impact of temperature is affecting the marine environment during high temperature. So what happens when the temperature is rising? There is a lot of changes in the currents as well as the melting of glaciers. So these things bring a lot of waters into there is a lot of movement of water mass from one place to another, especially into the fjords. The Atlantic water intrusion, which is warmer in nature, is much more. So that makes the fjords like from Arctic dominance to Atlantic dominance. And because of high glacial meltings, a lot of nutrient and turbidity comes into the environment, and which changes the JDU means the euphotic zone, means to where the light passes through, and subsequently it can create a steep gradient of hydrographic parameters like nutrients, temperature and salinity, and that in turn will control the phytoplankton to thrive in. So what I am going to explain is there are two fjords in Svalbard, which is called Kongsfjorden and Krossfjorden, which is basically fed by a single mouth. But what I am going to show here is, even though they are fed by a single mouth, the impact of or the settings in the two fjords are quite dissimilar, and they have different response to the changes in climate. So there are a field campaign took place in 2018, and we sampled the fjord in 2 phases in a gap of 10 days. So I am going to show how the fjord responded in the gap of 10 days. So coming to hydrographic nutrients, if you see the left panel in the top, left side in the top panel, so there are phase 1 and phase 2, and first upper 4 panel is Kongsfjorden. You can see that even in the 10 days gap, the intrusion of water is much clearer than previous like phase 1. So what I mean to highlight here is the intrusion of Atlantic water into the fjord is very clear, even though there is a gap of 10 days, and there is a clear indication of that in the Krossfjorden, the distribution of the hydrography and is much more similar compared to much more homogeneous compared to the Kongsfjorden. So we can see that even the mouth of the fjord, like outer fjord, have lower salinity. So that might be intriguing to you, how when the Atlantic water is entering in the mouth, how the salinity can be lower. Actually, in fact, there are some huge glaciers which is melting into the mouth, and that is changing the Atlantic water impact, and thereby the salinity is quite low. And regarding the nutrient is quite limiting there. That means nitrate and silicates are quite limiting, so that is not favorable for growth of larger diatoms, but it can sustain the non-siliceous phytoplanktons, which are larger in size but not very effective in fixing the carbon dioxide. So these are the picture panels which shows turbidity and CDOM. CDOM is nothing but the colored digital organic matter which competes with phytoplankton. Phytoplankton prefers light in blue wave bands to fix the carbon dioxide. But CDOM is such a factor which competes with and take away the blue lights. So this is one of the major component we should look into, so that if we are into quantify the carbon fixation by phytoplankton. So what I can highlight here is, if you see there are some red colors in the inner fjord, that means the glacial melt, and the glacial melt is contributing towards turbidity as well as sea dome, and thereby decreasing the productivity in the inner fjord, because outer fjord is free from all those kind of influences. And in the right hand side, the cross fjorden, you don't see such high like stratification or high changes or gradient in the fjord. That means the fjord is more or less homogeneous compared to the Kongs fjorden. So the regression figure shows that the salinity and sea dome and turbidity has an inverse relationship. That means when the water is marine in nature, the concentrations of sea dome as well as the turbidity is less. That means the productivity will be much better towards the outer fjord than compared to inner fjord. So this diagram shows the phytoplankton biomass and grazing by zooplankton. So we can see that left side panel is from Kongsfjorden and right side is Grossfjorden in two phases. Upper phase is phase 1 and down is phase 2. So there is a contrasting characteristics you can clearly observe. And if you see the regression figures, we try to explain the grazing impact on phytoplankton. We know that zooplankton grazing, measuring zooplankton grazing is a quite tedious job and very difficult to measure in situ sometimes. So can we do it in another way, like in optical method? So basically you can see there is a positive relation between the few pigments. Few pigment means when the phytoplankton pigments degrade, they reside sometimes in the water column, and we plotted it against par. So that shows a positive relationship. So the basic hypothesis behind it is, when there is a zooplankton grazing the phytoplankton, there is a fecal pellets are generated. If the fecal pellets are heavier in nature, they will sink faster when the macro zooplankton, that means bigger zooplanktons are eating on the smaller one. But when there is a smaller zooplankton, like micro zooplankton are eating on or grazing upon the phytoplankton, the fecal pellets will be lighter in nature, which can sustain in the water column for longer time. So that will give us a signature that how the what kind of phytoplankton or zooplankton is present in the in the water column. So even though we do not have direct measurements of grazing, but our colleagues from CMLRE did the grazing experiment in the same time, and that could substantiate that microzooplankton grazing was dominant during that time. So this figure shows about the phytoplankton pigment or the size distribution. You can see that from the left side is Kongsfjorden and right side is Grossfjorden. The phytoplankton size is mostly dominated by larger planktons, and when you go towards the mouth, the phytoplankton diversity is increasing. And when we plotted the light absorption efficiency of phytoplankton with chlorophyll, that means the biomass, we have a negative relationship or inverse relationship. So what happens when the size of the plankton is larger, the pigments inside the planktons are overlapped on each other. That means when the light coming from the sun, the efficiency of the light absorption efficiency decreases. That means the larger planktons are lesser efficient in fixing the carbon dioxide in the ocean. So that is called pigment package effect, and these are very, very crucial to be considered for when we are into modeling approach, like how what is the efficiency of phytoplankton to convert the carbon dioxide into oxygen or through photosynthesis. So this is one of the picture. We show the light absorption spectra. You can see Kongsfjorden is left side and right side is Grossfjorden. The light absorption spectra, that means the amount of light absorbed by the phytoplankton is much lesser in Kongsfjorden, and the turbidity is much higher. So that means the productivity is vice versa in these two fjords. So we also use a state-of-art technology called fast rate repetition rate fluorometer. So it gives a lot of physiological parameters which can be interpreted in a very different way and can give very crucial information about the marine environment. So the panels which shows that first one is light harvesting, that how much antenna is used by the phytoplankton to receive the lights. The second one shows how much light, what is the cross section of the light absorption. And third one is the how much light is being dissipated by the phytoplankton, because it is not always whatever light is received by phytoplankton is utilized for carbon fixation. Some of the lights are returned back to the nature. And the fourth panel shows what is the efficiency of the conversion of light energy into biochemical energy. And the last one is it shows the carbon fixation efficiency. So these kind of parameters can give us a very clear picture about what is happening in situ and in a very detailed manner, so that we can interpret the response of the environment to the changing parameters or surrounding parameters. And I conclude here. There are so many points, but I will try to highlight the final point, that even though the fjords are very nearby and fed by a single mouth, the impact of climate change can be very, very different when you are focusing on temperature changes or any kind of intrusion, Atlantic intrusion into the fjords. So the basic point I want to highlight here is, even though if we are focusing on the very similar area in a very separated by only 30 kilometers, the impact of climate change or the temperature can be very, very different if we are considering in future such kind of studies. So thank you for your attention.
Thank you, Dr. Tripathi.